I'm going to give you a list of steps that I think you should follow whenever you're solving a radical equation. Step 1, isolate a radical term on one side of the equation. To isolate a radical term means to get it by itself on one side of the equation. Now, for a lot of our equations, you will only have one radical. Okay, so isolate it. For some of the equations, for a few, you will have two radicals, and you'll have to decide which radical you'll want to isolate. It doesn't matter which one, just choose one of the radicals and isolate it. But for most of the equations you and I look at, there will only be one radical. Step 2, raise both sides of the equation to the power of the index. For most of the problems we'll look at, the index will be 2. These will be equations that have square roots, okay? Square roots. That means the index will be 2. So when they say raise both sides of the equation to the power of 2, that basically means square both sides. I will show you one example where the index is 3 and you'll have to raise both sides to the power of 3. You'll have to cube both sides. Step 3, if the equation still contains a radical, go back to step 1 and do these steps again. If it does not contain a radical, solve the resulting equation. The resulting equation could be a linear equation or quadratic. When you're done, step 4, this is a mandated step. This is not optional. Check the proposed solutions in the original equation. Okay? It is very possible that the proposed solutions are actually extraneous, which means they satisfy the manipulated equation but not the original. You want to make sure that you are submitting final answers that are solutions to the original equation. All right, here we go. All right, example 1, let's solve this radical equation. Now, like I said, there's only one radical here, and this is what we need to isolate, which means we need this minus 5 to be sent over to the other side of the equation. You can do that by adding 5 to both sides. So let's add 5 now, add 5 here, add 5 there, and what you get as a result is the square root of x minus 6 is equal to positive 5. Now step 2 says raise both sides to the power of the index. So the index here is 2. I know that because whenever the index is not written, it's assumed to be 2. So I'm going to square both sides. I'm going to square the right side. I'm going to square the left side. Squaring a square root cancels the square root out, and so you're left with x minus 6 is equal to 25. And then this is a linear equation, so I will isolate x by adding 6 to the right side to give me my proposed solution of 31. All right, my proposed solution is 31. It's now time to check my answer. All right, here's my original equation, and what I'm going to do is I'm going to substitute in my proposed solution of 31. Right, that's what we got. So I'm substituting in 31 in for the variable, and you're just simplifying the left-hand side and confirm that it's 0. So this gives us the square root of 25 minus 5 is equal to 0. The square root of 25 is 5. 5 minus 5 is 0. The left-hand side matches the right-hand side, so this is definitely equivalent. So what I can say confidently now, which I could not say before, is that x is indeed equal to 31. Okay? This next example has the square root of 2x plus 4 plus 2 is equal to x. Remember, step number 1 is to isolate the radical. In order to do that, I'll subtract 2 from both sides. On the left-hand side, now all I have is the square root of 2x plus 4. On the right-hand side, let's be careful. These are not like terms, so you do not get like, I don't know, negative 2x or anything like that. The only thing you can do here is rewrite this as x minus 2. Okay? Now the next step is to raise both sides to the power of the index. Now, the index here is 2. Again, for most of these, it's going to be 2. Let's square both sides. Now, you're going to have to be very careful about squaring the right-hand side. You're going to have to, you must, use parentheses here. What you do not want to do, let me show you. You do not want to just square x and square negative 2. That's not what we're doing. We're squaring both sides. So take that whole side and square it, okay? Squaring the left-hand side just cancels out the square root. So you're just left with the radicand. Now you have to be very careful here. Let me show you what you are not to do. You are not to distribute an exponent across subtraction or addition, right? So you do not distribute that negative. You do not distribute that exponent. Instead, what you should rewrite this as is x minus 2 times x minus 2. After all, that's what it means. An exponent means repeated multiplication. And so I'm copying down the left-hand side. Nothing changes there. But on the right, some of you know this as FOIL. So it's distribution, okay, like that. And so you and I get x squared minus 2x minus 2x plus 4. In other words, we get x squared minus 4x plus 4. That was combining these two like terms. Now notice that the resulting equation does not have a radical at all. That's good news. Furthermore, please also notice that you have a 4 on the right and a 4 on the left. That cancels out those two terms. A third thing to notice is that this equation is quadratic. And whenever you have a quadratic, it may be a good idea to set this equal to 0. So what I'm going to do is I'm going to move all of my terms to one side. Now, I've chosen to move everything to the right. Since there's a lot more terms over here, I'll just move this one term over here, and that'll give me a 0 on the left is equal to x squared minus 6x. Whenever you have something quadratic, you're going to want to set it equal to 0 and try to factor. Now, when you factor this binomial here, the GCF is x. So let's factor out the GCF. And next, you're going to want to use something called the zero factor property, where you set each factor equal to 0 and solve. So I'm going to set x equal to 0 and solve. I'm going to set x minus 6 equal to 0 and solve. So x is equal to 0 or x minus 6 is equal to 0. That gives you either x is positive 6 after adding 6 to both sides, or it's 0. So these are your two proposed solutions, 0 or 6. And what we want to do is substitute them into the original equation, which says the square root of 2x plus 4, right? And then it said plus 2 is equal to x, right? So what I'm going to do is I'm going to substitute, and I'm going to check 0 first, okay? So 2 times, I'm going to plug in 0 right there, plus 4, and then plus 2 is equal to 0, well, supposedly, right? So let's simplify all this and see what we get. The radicand, 2 times 0 is 0. 0 plus 4 is 4. So then this just turns out to be the square root of 4. And then when you add 2 to it, supposedly you get 0. The square root of 4, though, is 2. Plus another 2. Does that give you 0? No, of course not. This gives you 2 plus 2 is 4. So this is a contradiction. So what I'm going to do is I'm going to go back to this solution, x equal to 0, and I'm going to label it as extraneous. What this means for us is that x equal to 0 satisfies the manipulated equation, which is here, right? This is the manipulated equation, but it does not satisfy the original. This is the original. That's what extraneous means. So x equal to 0 is not one of your final solutions. All right, let's check x equal to 6. Checking x equal to 6. Here's my original equation right up top here. I'm going to plug in 6 now and see if it works. Okay, I've plugged in a 6. That gives me the square root of 16, because 2 times 6 is 12, plus 4 is 16. So the square root of 16 and then plus 2 more is supposedly 6. The square root of 16 is 4. So 4 plus 2 is 6. That is true, right? That is true. So then my one and only solution is x equal to positive 6. Here's the next one. This would be a really good example for you to pause the lesson, pause the video, and to try this on your own. So why don't you go ahead and try this by yourself first. All right, so I hope you paused the video and tried this on your own. So you should have subtracted 50 from both sides, and then that gives you the square root of 9m is equal to negative 9. I want you to know that I can already see that the answer here is no solution. And I know it's no solution because remember back in chapter 9, section 1, I taught you how this means the principal square root. That means the positive square root of something is negative. That doesn't make sense. Something positive cannot equal something negative, right? So I can already tell that this statement does not make any sense. Actually, you can figure that out in the original statement without having to do anything. The only way you can add something to 50 and end up with 41 is if you're adding a negative value, right? If you're at 50 units, the only way you're going to go down to 41 is if you are adding a negative value. But this is defined to be something positive because this symbol means the principal square root or the positive square root. So there's no way you're going to add something positive to 50 and end up with 41. That just doesn't make sense. If I keep following my steps, however, I would, like, if you didn't realize that, that's okay. What we can do is we can square both sides, put parentheses around negative 9, please. I hope you use parentheses there. This squaring of both sides leaves you with 9m is equal to positive 81. And then when you divide both sides by 9, you get a proposed solution of 9, positive 9. Now we have to check this. All right, so here we go. All right, this is what the checking process looks like when I plug 9 into the original equation, and I end up getting the square root of 81, and then plus 50 is 41. The square root of 81 is 9. 9 plus 50 is 41. That is to say 59 is 41. No. That's not true. This is a contradiction, right? This doesn't work. So then my proposed solution, m equal to 9, is extraneous. The one and only proposed solution that the algebra gave me doesn't work. It's extraneous. So that means my final answer is no solution. All right, everybody, good job. Next example, you have x cubed plus 27. All of that raised to the power of 1/3 is equal to x plus 3. Some of you might be thinking, wait a minute, we're supposed to be solving radical equations. Where's the radical? Well, we learned in a previous lesson that a rational exponent can be rewritten with a radical. So I'm going to rewrite this as x cubed plus 27, all of that underneath a cube root. All right. Now there's only one radical here, and it's on the left-hand side of this equation, and it's already isolated. So what we can do right away is raise both sides to the power of the index. Now, in this example, the index is 3. So we're not squaring both sides, we are cubing both sides. Now, cubing a cube root just leaves you with the radicand, okay? And this right-hand side, x plus 3 quantity cubed, really is x plus 3 times x plus 3 times x plus 3. I could barely fit it there, right? So you have to distribute. It's a whole lot of distribution here in order to get what the right-hand side should be written as. So one thing I recommend to do is distribute two binomials first. I should have said multiply two binomials first, and then we'll multiply by that last binomial last, okay? So multiplying the two binomials on the back end there will give you the following. The left-hand side is what it is. This binomial is still there. All right, here we go. X squared plus 3x plus another 3x plus 9. That's foiling, by the way. Some people know it as foiling. Combining like terms gives you x squared plus 6x plus 9. Now, let me make some of this a little cleaner here. Make sure it's clear what I'm writing. Make sure this looks like a 3 there. Make sure I'm not misleading anybody. All right, now what you want to do is continue distributing. Distribute an x, and then distribute a 3. Okay? The left-hand side is what it is so far. Copy that down again. Now here we go. Distributing an x gives you x cubed plus 6x squared plus 9x. Again, my squared here looks pretty sloppy. Hold on. There. Now distributing a 3 gives me 3x squared. I'm going to stack that underneath its like term. 3 times 6x gives me 18x. And then 3 times 9 is 27. So then I end up with x cubed plus 27 is equal to x cubed. Now I stacked my like terms. So I'm combining those two, and I'm combining those two, okay? So I end up getting plus 9x squared plus 27x, and then plus 27. Now, this equation happens to be cubic at the moment. However, notice that x cubed on the left and x cubed on the right, and 27 on the left and 27 on the right, they all cancel each other out. All you're left with on the left is 0, and on the right is 9x squared plus 27x, which happens to be quadratic. In the previous example, we said let's try factoring whenever you have something quadratic. Well, we said set it equal to 0. This is already set equal to 0. And then factor. The GCF here is 9x, leaving you with x plus 3, right? And then you're going to want to set each factor equal to 0 and solve. So one factor is 9x. The other factor is x plus 3. After dividing both sides by 9, you get 0 divided by 9, which is just 0. After subtracting 3 from both sides, you get x is equal to negative 3. Now, these two solutions should be checked. Now, I can tell you right now that both of them will work. And I know that because you and I cubed both sides. And what I know to be a fact is that whenever you raise both sides of an equation to an odd power, you will not get something extraneous. The only chance of you hitting an extraneous solution is if you raise both sides of the equation to an even power. So basically for us, whenever you square both sides, you have to check for extraneous solutions. But if you cube both sides, your answers will work. But just to be really thorough, I'm going to check my answers, all right? It won't take us long at all. All right, the original equation said x cubed plus 27 raised to the power of 1/3. 1/3. Okay, a lot better, is equal to x plus 3. Now what I'm going to do is I'm going to substitute in 0 first, okay? So then you'll have 0 cubed, right? And then plus 27, that raised to the 1/3 power, is supposedly equal to 0 plus 3. Okay? All right, let's do it. Now 0 cubed is 0. 0 plus 27 is 27. So this is 27 raised to the 1/3 power, supposedly is 3. The 1/3 power is the same thing as the cube root of 27 is 3. Now you and I know that the cube root of 27 is 3. So then this definitely checks out. X equal to 0 is good. All right, I can come over here. up here, and I can box this as a legit answer. The only other value I need to check to make sure that it works is x is equal to -3. Why don't you pause this video and plug in -3 into the original equation and verify that it works. All right, here we go. So -3 cubed is -27. -3 plus 3 is 0. Now -27 plus 27 is 0. So the cube root of 0 is 0? Yeah, 0, 0. That's true. This works as well, right? So I can come up here and confidently box the other solution as well. All right, good job, you guys. In example 7 here, you have the square root of 3x plus 21 is equal to 3 times the square root of x minus 5. Now, for the first time, you have two radicals. Which one should you isolate? Well, the first one, because on the left-hand side, because it's already isolated. If you chose to isolate this one, you'd have to divide both sides by 3. You're going to get 1/3 over here as a fraction. That sounds like a mess. This one's already isolated, so why don't you start there? So step 1 is done for you. A radical is already isolated. So let's raise both sides to the power of the index, which in this case is 2, right? These are square roots. So I'm going to square the left-hand side and the right-hand side. Now squaring the square roots leaves you with just the radicand. But on the right-hand side, you have more than just a square root. You have 3. You have to square the 3 as well. So 3 squared is 9 times just x minus 5, just the radicand. So then you get 3x plus 21. You're going to want to distribute that 9 to get 9x minus 45. Now what you're left with is a linear equation, so collect all of your variables on one side and your constants on the other. It doesn't matter what side of the equation you collect your variables on, so I'm choosing the left-hand side here. Of course, you can do something different. I end up with -6x plus 21 is equal to -45. I am going to subtract 21 from both sides in order to move all my constants to the right. I get -6x is equal to -66. When I divide both sides by -6, I get that x is supposedly equal to +11. So what I'm going to do now is I'm going to check my work, all right? And the way I'm going to do this is by going to the original equation, and I'm going to plug in x equal to 11. Now this is a great spot at which you can pause this video and do this on your own and confirm that 11 is indeed the solution. Now here's the original equation. I hope by now you have substituted, right, and verified. So then this is 3 times, and then we have an 11 here that we're plugging in, plus 21, square root of all that, is supposedly equal to 3 times the square root of 11, and then minus 5. All right, let's verify. 3 times 11 is 33, plus 21 is 54. Okay, is supposedly equal to 3 times the square root of 6. The left-hand side by the product rule for radicals can be rewritten as the square root of 9 times the square root of 6. The right-hand side is just 3 root 6. The square root of 9 is 3, so it's 3 root 6 on the left, 3 root 6 on the right. These are definitely equal to each other. It checks out. So now I can go to my proposed solution and say, yep, x equal to 11. X equal to 11 is indeed the one and only answer. Here's the last example for this section, for this lesson, and notice again that there's two radicals. Now neither of them are isolated. You have to choose which one to isolate, and it doesn't matter which one you're going to isolate. The first one that you choose to isolate will be eliminated first, so let me go ahead and isolate this one. I don't know. You could definitely, do something different. But I'm going to isolate this radical, which means I'm going to get rid of this one by using the inverse operation of addition. I'm going to subtract the square root of 9x from both sides. All right, the left-hand side, you have a radical that is isolated. Let me come over here and make room. So you have the square root of 9x plus 16. And on the right, of course, these two terms are not like terms. So the best you can do is just write it as 8 minus the square root of 9x. Now it's time to raise both sides of the power of the index. Now, in this example, the index is 2. These are square roots. So I'm going to square the left-hand side, which basically leaves me with the radicand. I'm going to put parentheses around the entire right-hand side so that I can square it. Now, the left-hand side is just 9x plus 16, but the right is really 8 minus the square root of 9x times 8 minus the square root of 9x. It is imperative that you write that down correctly and understand how it is we are going to simplify that right-hand side. Now, the left-hand side is just 9x plus 16. Okay, we can just kind of bring that down. But the right-hand side, we're going to have to FOIL, right? We're going to have to multiply 8 times 8, and then 8 times negative root 9x. Let me do that part first. 8 times 8 is 64. 8 times negative the square root of 9x is just negative 8 root 9x. And then you have negative root 9x times 8 and negative root 9x times negative root 9x. So the first product is negative 8 root 9x, right? So you get that same term again. And then finally, a negative times a negative is a positive, and a square root times another square root is just going to cancel out the square roots and leave you with just positive 9x. Okay? Barely. Okay, now notice a few things. Notice that there's a few things that you have to notice. 9x and 9x cancel, right, everybody? Furthermore, please notice that you are still left with some radicals, all right? Actually, these two radicals are like radicals. Do you remember that? Like radicals should be combined by adding their coefficients, negative 16, right? Times the square root of 9x. So this is what you have at this point. Now, the instructions in the very beginning of the lesson said, if a radical remains, repeat step 1. Go back to step 1. Step 1 is isolate a radical. So now we have to isolate this radical, get it all by itself. Let's start doing that by subtracting 64 from both sides. 16 minus 64 is negative 48. We almost have the radical isolated. What we should do now is divide both sides by negative 16. And that will isolate your radical. On the left-hand side, you'll end up with positive 3 is equal to the square root of 9x. Now that this radical is isolated, we can get rid of it by squaring both sides, raising both sides to the power of the index. The left-hand side is 3 squared, which is 9. The right-hand side is just 9x. This is a linear equation. We can solve it by dividing both sides by 9, and we get a proposed solution of x equal to 1. Okay? 1 is equal to x, which is the same thing as saying x equal to 1. Now, this is a proposed solution. We did raise both sides of the original equation by an even power. So you should check, absolutely, after all of that squaring that we did, we should definitely check to make sure that x equal to 1 is indeed the solution. Here's the original equation. This is the original equation. Make sure I wrote it down correctly. Yeah, we're good. So we're going to substitute in 1 here, all right? We're going to substitute in 1. Wherever there's a variable, we'll substitute in 1. All right, here we go. So 1 goes in for this x, 1 goes in for that x. And what you end up with is, let's see, of course 9 times 1 is 9. 9 plus 16 is 25. So this ends up being the square root of 25, and this is the square root of 9. So you end up with the square root of 25 plus the square root of 9 gives you 8, supposedly. The square root of 25 is 5. The square root of 9, the square root of 25 is 5. The square root of 9 is 3. 5 plus 3. Yeah, that's 8 indeed. This definitely works. This solution here, this proposed solution, is my one and final answer.